guys, in this lesson we are continuing with volumes. This time though, we are not doing volumes of circular discs or circular washers, and that's because we're not going to be revolving a shape around an axis of rotation. That's not going to happen. What we are going to have is these cross sections that are different shapes. I'm going to zoom in a little bit here. This is a picture that a different teacher did, the one who made these lessons. He drew an f of x shape and he drew a g of x shape. And then he took Post-its and he cut those Post-its so that the base, the part of the Post-it that was touching his paper, went just from f of x to g of x. So that distance right there between f and g is called the base of that shape. Okay, this would be the base of the shape. Again, this is squares in this case. This is the base of that square at a different x value. So notice that this x value and this x value, we have two completely different lengths. That's okay because we're not going to subtract this y value minus this y value to find the distance. We're going to subtract the functions. So f of x minus g of x would find that distance. Okay, now we are going to reuse a method that we used back with circles in that previous lesson where we found volumes. We are going to find the area of a shape. In the previous one, we found areas of circles, and then we multiply it times this extra little distance, and we're going to use that extra little distance, that dx, to give each little square or whatever that area is some volume. So we end up with a volume instead of an area, right? We take our two-dimensional shape, multiply it times dx to get a volume. And then we're going to add up all of our volumes by using an integral. Okay, and that integral just takes every single little possible square tile, adds them all up, and then you get the total volume for every single square. Now, all of these squares are separated from each other, right? This guy who made these shapes cannot possibly have enough shapes to fill up. Like, he can't get an infinite amount of Post-its to fill up this this shape right here. He can't do that. So he's just showing you several of the squares that he could possibly get. Okay, so big takeaways from this. The distance from the bottom function to the top function is f of x minus g of x. So we're going to see that here. Ta-da! This is going to be f of x minus g of x, and that's going to be the base of that square. So when we talk about base, we're not talking about base from the square formula. We're talking about the base that is touching our paper. Okay, the piece of the Post-it that is touching the paper. That's going to be this right here. Now, we are going to find the area of a square. And how do you find the area of a square? The area of a square is side times side. So we have to figure out what this side is, and this side is also f of x minus g of x, because these two sides must be congruent because it's a square. Squares have congruent sides. Okay, that means the area of a square is side squared, that's the formula, and one side is f of x minus g of x. Okay, that's how you get the area of a square. Now we talked about for volume, we have to multiply times that tiny little thickness that is going to be infinitely small, super, super small, and that thickness itself is going to be dx. So the volume of one of those little square tiles is f of x minus g of x squared times dx. That's one square. But we have to add up all of the cross-sectional areas as volumes So we stick a little integral sign there, and then we put a down at the bottom and b up at the top like we've done for every single problem so far. Okay, a is the furthest left where your two shapes intersect. B is the furthest right where our two shapes intersect, our two functions. So that would be, here would be that a value, which is probably about 0, and then our b value would be this x value. This is a, and this is b. Awesome. So that's how you find volume of cross sections that are squares. It's always going to be this formula for squares. Let's move on to cross sections that are isosceles right triangles. Okay, so that means that when we take our shape, which is actually like in this direction, here's our x-axis and here's our y-axis. We have our top function, which is f of x, and our bottom function, which is g of x. The base of those isosceles right triangles is here. That is this distance, the base of an isosceles right triangle. Now again, that is not be the base in the triangle formula necessarily. If our triangles were resting on this hypotenuse, that would be considered the base that is touching your paper. So just be careful with what is the base that is touching your paper. That's what you're going to use for f of x minus g of x. So top function minus bottom function. The higher y value minus the lower y value. Here again is a, and here is b. Okay, so how do you find the area of a triangle? Well, it's base times height divided by 2. Okay, isosceles triangles mean that these two sides that meet up at your 90-degree angle are identical to each other. So the base and the height have the same value. Area of a triangle equals 1/2 times base times height. Base in this case is this distance because this is the piece that was touching our paper. Okay. If it was the hypotenuse, it would tell you that the hypotenuse is the piece that is touching the paper. It would literally say hypotenuse or longest side or something like that. Okay, so f of x minus g of x and f of x minus g of x are going to substitute in here for b and for h. So the area of one triangle is 1/2 times f of x minus g of x for this length, and f of x minus g of x for this length, that height right there. That on our picture is the piece that is coming out from our paper. It's the one that's like sticking straight up. Now, of course, you might notice that both of these sets of parentheses are identical. So that area is 1/2 times f of x minus g of x squared. And you could, of course, take a look at the area of a square and realize that an isosceles right triangle is exactly a diagonal cut of a square. So it should be 1/2 of a square formula, and it is 1/2 of a square. Beautiful. Okay, so we got to give it some volume. The volume of one isosceles right triangle tile, got to give it thickness, is 1/2 times f of x minus g of x squared. That's the area times dx is that thickness. Okay, you have a choice of where you can put that integral symbol. You can put it in front of the 1/2, or you can put it to the right of the 1/2, because a half doesn't have any x's, no variables with it. It really doesn't matter. I'm going to put it here. Why not? From A to B. Okay, generally you're going to have these problems on a calculator section unless this is a really easy function to subtract so that you can then square it. Okay, so it would be like nice and easy polynomial style function so that you can square. Awesome. Next. Next page says cross sections are equilateral triangles. So as you slice, we get an equilateral triangle. Equilateral means that all three sides are identical. Okay, the base of an equilateral triangle is going to be f of x minus g of x. This is our base again, the piece that is touching our paper. Piece of the Post-it that's touching the paper is this f of x minus g of x. But the area of a triangle equals 1/2 times base times height. So if this guy is the base, we have to figure out what the height is. Now, we know that the sides are all the same, so this is f of x minus g of x, and this is f of x minus g of x, but the height of a triangle is going to be its altitude, this guy right here. It's got to have that 90-degree angle to it, and this is not a 90-degree angle right here. It's going to be a 60-degree angle. Okay, so if this is a 60-degree angle, that makes this guy a 30-degree angle, and that's a 90-degree angle. That's a 30, 60, 90 triangle. Okay, so we're getting somewhere. We're trying to figure out what is this height. I'm going to call that guy H in our picture. Okay. In a 30, 60, 90 triangle, our shortest side goes from here to here. The hypotenuse is 2 times the length of this short piece, and then this is the square root of 3 times this short piece. So the H is going to be the square root of 3 times, and this little guy, this pink bit, is f of x minus g of x divided by 2. 1/2 of f of x minus g of x. So that's going to simplify to root 3 over 2 times f of x minus g of x. Awesome. Cool. If you are big into memorizing formulas, this is going to show up anytime there is an equilateral triangle. You will need this. If you're good with, I remember my 30, 60, 90 triangle ratios, awesome, you're good with that. Just repeat this every time you need it. Otherwise, memorize, because they would not give you this bit of information on the AP exam. All right, triangle. The area of a triangle is 1/2 times base times height. So it's going to be 1/2 times, our base was f of x minus g of x. And the height, h, like we talked about, is root 3 over 2 times f of x minus g of x, which simplifies into root 3 over 4 f of x minus g of x squared, because again, there's 2 of those f of x minus g of x's. Cool. I do not personally have that one memorized, but notice that it's just like the f of x minus g of x squared thing times, and in this case, it's root 3 over 4 for an equilateral triangle. So it's just the little coefficient that's changing up each time it looks like. All right, let's volumize this. Root 3 over 4 f of x minus g of x squared dx to give it that little bit of volume, that little thickness. Stick an integral here or here, put a little a to b, and you are done. Last one, cross sections that are semicircles. All right, so this one is different from the revolutions for several reasons. One reason, the base is on the paper and your shape does not go through the paper. In revolutions, you have all 360 degrees. In a semicircle, you only have the 180 degrees, this bit right here, which is the base of our shape. So every single piece that we see is going to be a semicircle. Another thing that's going to be different is the base is going to be the diameter. That's an annoying part that a lot of students forget. They talk about that base and they use it as the radius. So that's an issue. Here, f of x minus g of x is the diameter, which means that the radius equals f of x minus g of x over 2. Big deal there. Okay, f of x is our top function, g of x is our bottom function. That's the diameter. So to get the radius, you have to divide f of x minus g of x by 2. Usually, you're not going to actually be able to divide that by 2. You're going to end up taking that 1/2 out as a coefficient. It's pretty common. Okay, so how do you find the area of a semicircle? That depends. How do you find the area of a circle? Area of a circle is pi r squared. So a semicircle would be 1/2 pi r squared. Okay. Our radius, we said, is f of x minus g of x over 2. So I'm going to substitute in, instead of r, f of x minus g of x over 2. And let's go ahead and put that pi on top of that 1/2. There it is, pi over 2 instead of 1/2 pi. Okay, that r, we said, was f of x minus g of x over 2. And since it's radius squared, we have to square that set of parentheses. Okay, let's simplify this as much as possible. Squaring a fraction means you multiply top times top and bottom times bottom. So you square the top and you square the bottom. So this turns into pi over 2 times f of x minus g of x squared over, and then 2 squared is 4. And let's just go ahead and pull that 4 out over here with the 2, bottom times bottom. So this turns into pi over 8 times, and then with no needed denominator, this just becomes f of x minus g of x squared. So again, it shows up where we have an f of x minus g of x squared, and then it has a coefficient. So if you're all into the memorizing, f of x minus g of x squared, the coefficient for a semicircle is pi over 8. Cool. Let's toss this down here with some volume. Volume is going to be pi over 8 times the integral from a to b of the area, f of x minus g of x, always squared, and then dx at the end, because that gives us that thickness to get a volume going. Okay. So we might notice some things about integral defined functions for finding the volume of solids with certain cross sections. What we should notice, really important, is that to get a volume, the sum of the volumes, we take the area, multiply it times dx, and then you take the integral from a to b. The extra little thing that we talked about is that it is pretty much always going to end up being volume equals some coefficient times the integral from a to b of f of x minus g of x, in brackets, squared dx. And that coefficient depends on the shape. Okay, so if you want to memorize them, go for it. But it is totally possible that you could get some other kind of a shape that you didn't have memorized on an actual exam, such as we talked about getting a isosceles right triangle, but instead of it being this side, like one of the legs of that right triangle is the base, it ends up being the hypotenuse. I don't think we have any of those specifically on, we don't have any of those specifically on our notes, so perhaps I'll just do a random example of that at the end. Okay, next page. We have a region R that is bounded by y equals the sine of pi x and y equals x cubed minus 4x. So we need to find the two spots for A and B where our two graphs intersect each other. A is 0 and B equals 2. It is completely possible that you would have to find those 2 points of intersection by setting your two equations equal to each other, either by hand or in a calculator, right? Set this as y1, this is y2, and then hit second trace to get to that calc menu, hit 5 for intersect, and find one or both of those points. 0 is usually a pretty common one because that is an easy number to plug in. All right, but we are given those two values this time. Hooray! Okay. Hopefully it's pretty obvious. The sine guy is going to be this curvy guy that looks a lot like sine, and then this guy down at the bottom is going to be our x cubed minus 4x. I'm going to put this one as f of x since it is on the top, and this one is going to be g of x since it is on the bottom. If you want to go ahead and pause and plug this guy in as y1 and this guy in as y2 into your calculator, now's a great time for that. Fantastic. Okay, our job is to find the volume of the solids formed whose cross sections are the shapes indicated below. So we're using one picture for 6 different shapes. The cross sections are perpendicular to the x-axis. Okay, so the perpendicular to the x-axis thing tells us that here's the x-axis, so here is going to be, at a 90-degree angle, our cross section. Right, 90-degree angle. This is going to be the slice that we take out, which means that this little guy is dx. Okay. If we are told that we are taking our sections perpendicular to the y-axis instead, our shape would be this way. So we would subtract an f of x over here minus a g of x over here. It would look a little bit more similar to a few pages ago in a different lesson. Let me see if I can find it real quick. This one. This is one where we revolved around the y-axis. Our shapes would be cut this way, perpendicular to the y-axis. And that's because this was like f of x and this was g of x. So f minus g would be the height, well, really the base of our shape. And then this would be a dy. So height, base, and dy. Cool. All right, this time on A, we have cross sections that are equilateral triangles. Our equilateral triangle formula. Volume equals, we're an equilateral triangle. It was the root 3 over 4. That's root 3 over 4 times the integral from 0 to 2 of f of x minus g of x. F of x is sine of pi x, and then subtract x cubed minus 4x, square it, and then put a dx, always squared. Cool, you're gonna plug that guy into your calculator. If you had y1 as this and y2 as this, you should be able to plug that into your calculator like really simply. Grab my calculator. Sine of pi x and x cubed minus 4x. Okay, here's a little trick. If you're doing a bunch of these, just ignore your coefficient and then multiply times that at the end. So I'm going to do math 9 to get my integral from 0 to 2. Then I'll type in y1 to get to y1. There's a few different ways to do that. I like to hit alpha trace to get to that F4 menu. And here's y1. And then minus y2, alpha trace 2. I did not put parentheses around this. That's going to cause some issues. because we're going to have to square this, and there's no extra set of parentheses here, so I'm going to have to go all the way left to right there and insert a set of parentheses. Insert is on the delete key, so I'm going to hit second and then delete to get to insert, and insert another set of parentheses. And then we're doing dx because those y equations were in terms of x. Hit enter. It does not like something I typed in. y1 minus y2 squared dx from 0 to 2. What does it not like? Oh, because I plugged it into the wrong spot. Okay, well, let's fix this. Looks like it's going to be y2 minus y3. Let's troubleshoot. Why not? Hopefully you guys typed it in the right spot, but I'm going to go over to where I've got my y1 and replace it with a y2, and then I'm going to subtract y3. Okay, so I got 9.978, and that is the integral from 0 to 2 of f of x minus g of x in parentheses squared dx. However, there's this coefficient of root 3 over 4. Here's another calculator trick. If you're going to be using the same number over and over, you can store that number using this STO. You may have never seen this before. Click on that STO. And it says we are storing the answer as, and then you get to pick a letter. Let's plug it in as L. Why not? I don't know. L. L is here. I have to hit alpha, and then that key to get to L was the alpha key, and then the close parentheses key gets me an L. But you can really type in any of those numbers that you feel like. Could have done A for area, or V for volume, because it's volume, Miss Campbell. Duh. Okay, so anytime I type in an L, it's going to now type in 9.978 for me. Or you can just literally type this in every time you need it. You do you. Okay, so I'm going to take L and I'm going to multiply it times the square root of 3 over 4. Notice that I got out of that square root before I typed the divide. And then I'm going to multiply this times L to get back to L. I hit alpha and that close parentheses, and then hit enter. Okay, square root of 3 over 4 was a fraction that was less than 1 by quite a bit, so I got 4.3. 4.321. Okay, you could have tried to take this by hand, but I think since it's squared, you would have ended up with some really weird stuff and some U substitution. I'm not sure it would have worked out. Generally, if there's like signs and variables for like a polynomial and it's squared, they'll let you have that on a calculator problem. Okay, cross sections are semicircles. So again, our volume is going to be some coefficient times the integral from 0 to 2 of f of x minus g of x, sine of pi x minus x cubed minus 4x, bracket squared dx. Okay, and then we have to multiply that times some coefficient. What is that coefficient for semicircles? Semicircles is pi over 8. Okay. So you've got several ways to get that pi over 8 multiplied times that integral up there. You could go up here to the integral and like highlight it. Hopefully you can see that it's in blue. Yep. And hit enter and it brings it down here. And there you have it again. But it, of course, has to recalculate it in your calculator. Then you can multiply times pi over 8. And you get 3.918. Or I can type in L and multiply that times pi over 8. Pi over 8 times alpha, close parentheses for L, and you get the exact same thing because L is this 9.978 value. Awesome. 3.918. 3 decimal places, guys. All right, I suggest trying the next two and then double checking with the video. Right triangles, it was 1/2 as that coefficient. 0 to 2 of area of a square, sine pi x minus x cubed minus 4x, bracket squared dx. So I'm going to do L divided by 2. You can also store values as x, and you don't have to type in the alpha, L, or whatever. You can store as x. 4.989 for C. And if it's just a square, it is literally just 0 to 2 of, since we labeled our functions f of x and g of x, if you say let f of x equal sine of pi x, and let g of x equal this function, you can use f of x and g of x, even though the problem didn't give you that. But you have to say what they are. Let this function with that letter equal that function specifically. So now I can write in f of x minus g of x, be a little lazier about it, squared dx. Okay, this is the area of a square, so no coefficient is needed. The coefficient for a square is really just a 1, and that was the 9.978. We did not have to do anything for that one. Cool. All right. E and F. E and F are a little bit weird because these are rectangles and they give us something different. So these are not generic shapes that are really simple, like the square or an isosceles right triangle or equilateral triangle or a semicircle. They give us rectangles whose height is twice the length of the base. So we're going to have to go back and figure out the area of the rectangle that they're talking about. I'm going to draw my rectangle up here. I suggest drawing out your shape. Okay, the base, when they say base, they are talking about the f of x minus g of x bit. That's the f of x minus g of x. So here's the base, which is going to be f of x minus g of x. And then we have a height for that rectangle. We are told that the rectangle has a height that is twice the length of the base. So if our base was 1, the height is 2. If the base was 2, the height is 4. So let's draw the height twice as big-ish, whatever, not to scale. So that height is going to equal 2 times the base. And the base is f of x minus g of x. Okay, so we have to find the area of our shape. How do you find the area of a rectangle? The area of a rectangle equals base times height. Okay, that one's easy enough, base times height. Our base is f of x minus g of x. And our height is 2 times the base. 2 times f of x minus g of x. Oops. Okay. So now it's all just rewriting this. We found the area. To find a volume, you would multiply that times dx. Just simplifying this up a little bit, I'm going to put the 2 in the front. And then we've got f of x minus g of x twice. F of x minus g of x. Having it twice means multiply it times itself, which is squared. And then dx. Okay, and like we talked about before, when we were coming up with our shape, we said that the height was twice as much as the base. So when the base was 1, the height would be 2. That area would be 2. You can kind of test out your formula. So 1 squared is 1 times 2, and a 1 by 2 rectangle would have area 2. If our base was 3, the height would be 6. 3 times 6 is 18. 3 squared is 9, and 9 times 2 is 18. So you can kind of test it out to see if you did it right. Okay, let's stick our integral sign there. Integral, we are again going from a to b. Those are just the x values that we're starting at and ending at. Okay. We already know that f of x minus g of x squared bit from a to b is that 9.978. So we are going to multiply 2 times that integral that we already have. Mine was L, so 2 times L is 19.95668, blah, blah, blah. So 66 would turn into 7. Fantastic. Okay. F, cross sections are rectangles again. So we have to find the area of a rectangle. Area of a rectangle is base times height. The base is again going to be f of x minus g of x. The height is 1/3 of the length of the base. So we're going to take the length of the base and multiply it times 1/3. 1/3 is a 3 times, and then the base was f of x minus g of x. So this is the base, and then 1/3 of the base, which hopefully that makes sense. If this is f of x minus g of x, this is 1/3 of that height. 1/3 times that base. Cool. Simplifying this out, we've got 1/3 as our coefficient. Integral a to b of f of x minus g of x squared dx to give it that little bit of a thickness. So this is going to be 1/3 L, or L divided by 3, which is 3.3261 would become a 6. And we're done with that. Okay, at this point, I'm going to go ahead and pause with what we're doing instead of going to the next problem. And let's talk about an isosceles right triangle where it's the hypotenuse. Going back to here, the hypotenuse is the base instead of one of the sides is the base. That's a pretty common one, but it's just a little bit weird. So we're going to get this shape again. Right triangle, those look about the same. Okay, here's our right triangle. I'm going to call those the same, give them a little congruency mark. That means that this is a 45-degree angle and this is a 45-degree angle. Anytime you have an isosceles right triangle, they are 45, 45, 90 triangles is another way to think of those. Okay, if I'm saying the base is the hypotenuse, that means that that base, this guy, hypotenuse, equals f of x minus g of x. Okay. So this is the piece that is sitting flat on the ground. It's flat on your paper. F of x minus g of x is this whole base. Well, to find the area of a triangle, you have to multiply the base times the height and then divide it by 2. So we've got to find that height. How do you find the height? That's a 90-degree angle. This is a 45. So we know that the height of this triangle is going to equal this little guy right here, because this little triangle is also going to be a 45, 45, 90, this little triangle. This one right here. 45, 45, 90 as well. And the distance from here to here is half of f of x minus g of x. So this height right here is 1/2 f of x minus g of x. Cool. So area of a triangle equals 1/2 times base times height. 1/2 times our base was f of x minus g of x. I feel like we're probably getting sick of writing that out. Times, and then our height of the little triangle is also the height of our big triangle. That height is 1/2 times f of x minus g of x. So it looks like 1/4 of f of x minus g of x squared. So an isosceles right triangle where the hypotenuse is the base, 1/4 is your coefficient. So our volume would be 1/4 the integral from a to b of f of x minus g of x squared dx. If you're going to memorize those, I would probably put them on some flashcards. Awesome. Okay, we got one problem left. It is our AP problem. Okay, this is the 2010 AP Calculus AB Form B. So you can probably find this by somebody else as well. However, since we have not done one of these AP problems together in a bit, let's go ahead and do it together. It also gets us with the, I think it's the last 3 lessons that we've done are A, B, and C. Usually these 3 things go together pretty well in AP problems, so they stick them in the same free response question. Okay, so we've got the figure R that is the shaded region in the first quadrant bounded by the graph of y equals the natural log of 3 minus x. That sounds like a curve. This guy right here is going to be this function. The horizontal line y equals 6, so that's going to be this guy, and the vertical line x equals 2. Since we know that this is in the first quadrant, this line right here, x equals 0, is going to be our beginning of our shape. So, and the vertical line x equals 0. Okay, find the area of R. Okay, an area, you just need like a Riemann sum type thing, but we are using integrals. So we want to find all the little rectangles from left to right, all the little rectangles here. Can we see that okay? Yeah. Okay, the height of those rectangles is going to be our top function minus our bottom function. Our top function is the line y equals 6. Let's name that function g of x. I'm going to use green for this guy. Let's do g of x. Green and the blue probably look pretty similar, but the pink is running out. Okay, there's g of x. And then let's say that this guy is going to be f of x in that lighter blue color. Okay, so that means that the distance from here to here is going to be g of x minus f of x. That is the height. Okay, so the height of each rectangle is g of x minus f of x. And the width of each of these rectangles is a sideways distance, which is a change in x values, which is dx. So area will equal the integral of f of x. No, g of x is the one that's on top, isn't it? G of x minus f of x times dx, the height times the width. That's how you find area, right? Height times width. The integral adds them all up. Well, adds up all what rectangles? Where do we start and where do we end? We start at x equals 0, because that's this vertical line, 0, until we get to x equals 2. That was where our shape ended. So from 0 to 2 of g of x minus f of x. Let's take a second and plug in how did I do it on here? Let's plug in f of x as y1, so that's going to be 4 times the natural log of 3 minus x. Put it in y1, Miss Campbell. 4 natural log of 3 minus x, parentheses. Good. And the horizontal line y equals 6, so that one's going to be in y2. And then quit out. Doesn't matter if you're in radians or degrees for this guy because there's no sines or cosines. I didn't mention it, but if you were not getting the same numbers that I got in on the previous page, you probably were in degrees instead of radians. Radians for calculus, please. All right, so we've got an integral, math 9, from 0 to 2 of, and I put g of x as y2 minus f of x was y1 dx, and we get 6.817. This is enough work for these problems. As long as you say what g of x and f of x stand for, which are these guys, you can put g and f instead of this, or you could have put 6 minus, I'll write it the other way. This is the same thing as the integral from 0 to 2 of g of x was 6 minus f of x was 4 times the natural log of 3 minus x, and then dx. So you can put the functions themselves or you can put the letters for the functions. It does not matter. AP does not like it when you put like y1 and y2 on your paper, even though that's what you're doing in your calculator. Okay, set it up actual mathy style. All right, part B. So part A was an area, part B is a volume. We are revolving about a line. So if we are revolving, that's definitely going to be area of a circle. It might be a disc or it might be a washer. Okay, so we need area of a circle, and then the volume is going to be that extra dx. The horizontal line is y equals 8. So over here in our picture, here was y equals 6. So y equals 8 is going to be just a little bit above that. Okay, so we're going to have to draw some different pictures. We are revolving about that line. So this line that was below is going to come up. Okay, so that's going to be one circle revolving. And then this curve that is down below is going to come up above. So it's going to look kind of like that. Yeah, that looks pretty good. And that one's going to revolve like this. Oh, that's definitely too tall. That's better. Okay, so we do have an outer circle minus an inner circle. So we need to find area of outer circle and area of the inner circle. The outer circle, we need to figure out the radius, the big radius. That is the radius that goes from the axis of rotation until we get to the function that is further away. Well, what's farther away from y equals 8? Is g of x further away or is f of x further away? Hopefully in your brain you're saying, obviously, Miss Campbell, it is f of x that is further away. So from axis of rotation to f of x, that is going to be our big radius. Big radius is distance from axis of rotation to f of x. And little radius is going to be distance from axis of rotation to g of x. Okay, to get a distance, you subtract. Well, normally we do higher numbers versus lower numbers. Since y equals 8 is physically on the graph above the f of x function, it's higher up. So we're going to do 8 minus f of x as big R. Big R equals 8 minus f of x. I'm sticking with my blue in case you can see it. Then little r is going to be, and again, we are going from axis of rotation, that distance right there, it's going to be 8 minus the g of x function. That is this tiny little distance right there. 8 minus g of x. Fantastic. So how do you find the area of a washer? Draw the picture of a washer. Okay, to find the area of this shaded region, you take the area of the big circle minus the area of the small circle. So area is going to be pi big R squared minus pi little r squared, which is the same thing as pi times big R squared minus little r squared. Okay. That is area. How do we find volume after we have area? Well, volume is the integral of area, as long as we give that area a little bit of a thickness, and the thickness is going to be dx. Since all of our radius stuff is in terms of x, this is going to be a dx. If we were revolving around the y-axis or something that was a line that was parallel to the y-axis, everything would be in dy's, and all of our functions for r would have to be in terms of y as well. Okay, since you put that r and little r equal these other functions, you do not have to rewrite the 8 minus stuff here in parentheses. But we are going to have to, in our calculators, go back and make y1 and y2 be different. So this is going to have to be 8 minus f of x. I'm going to use that insert that we talked about a little while ago. Insert is second delete, and I'm going to type 8 subtract, and then move down to the next bit. I'm just going to clear out this one. 8 minus 6. 8 minus 6, which is 2, right? Notice that this cylinder up here has a radius that is consistent all the way across. Okay, it's not like any other kind of vase where it gets like bigger or anything. It's not, well, this actually reminds me of like 4th grade volcanoes that we used to make out of, I don't know, like plaster. And then you would put the, can you see that? Little volcanoes? Put the vinegar and the baking soda in, and then it bubbles over. It's kind of the shape I'm envisioning here. Well, 8 minus 6 is just 2. Okay, so you absolutely could have just put 2 there. Cool. Quit out of that. Okay, this is different from when we were doing those square shapes. On the square shapes, we had parentheses squared. Like when we did the cross sections, it was parentheses squared. These, it's big R squared minus little r squared. So you got to do the squareds individually on this. That's a big difference. Okay, I'm going to go ahead and type in math 9. We're going from zoo. I haven't put in my limits of integration. Our smallest x value was 0, and our biggest x value was 2. All right. 0 to 2 of big R was my new y1. So I'm going to type in y1 squared minus y2 squared dx. And I found out you do not have to put in parentheses around your y1 and y2 when you square it. It just works out nicely. So this is 53.533 as the integral. And then we multiply times pi. So you can put 53.533 pi, or you can multiply it in your calculator. 168.180. Yes, even if you get a 0 at the end, you do have to write the 0. You cannot just leave it as 0.18. Awesome. Next is part C. Part C is what we learned in this lesson today. It says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Since it's perpendicular to the x-axis, it's going to be dx's. Okay, find the volume of the solid. Okay, since it is squares, we have to find the area of a square. Area equals something squared, right? That's how you find area. Okay, the distance we are talking about is the same as that distance that we did in part A. It's the green minus the blue, which is g of x minus f of x. So notice those letters switched up from the previous problems we had. In the previous problems, f was the top function and g was below. So it's g minus f squared, right? Because g minus f is that distance. So area of a square is g of x minus f of x squared. So if that's the area, the volume is going to be g of x minus f of x squared times dx. Because again, that thickness, the little bitty thickness of our tiles is dx, that distance between the two x values. That's the volume of one square tile. To add up all the volumes of all the square tiles, we got to take the integral. And again, we are going from 0 to 2 because that's the furthest left to the furthest right that our x values will go. It's like our domain. Let's type that in. Integral is math 9. We're going from 0 to 2. And we're doing g of x minus f of x and then squaring. So I'm going to put parentheses. This is going to be y2. Nope. I'm going to go in and hit delete a couple of times and get rid of all that other junk that I typed in for that earlier problem. Cool. That looks good now. So g of x was y2 now. y2 minus y1 parentheses squared. So I already typed in my parentheses first this time. It's the power of thinking ahead, huh? Awesome. 26.267. Volume equals 26.267. Fantastic. So we have finished up our entire lesson today, and that is our last official lesson of the school year. You guys rock. Have an awesome day.